Hi, everyone. My name is Dr. Cardona, and I have Joey Crenshaw here, who is the Spacecraft Operations Development Lead for the Joint Polar Satellite System project through NASA. And he will be presenting on his satellites. Go ahead, Joey.
All right, thanks. Yeah, like Dr. Cardona said, I am the spacecraft operations lead or operations development lead for the Joint Polar Satellite System. We're working with NASA, NOAA, and the Department of Defense to upgrade our weather satellite constellation. I'm working on JPSS 2 right now. I launched I worked on the JPSS 1 launch back in 2017 and the preparation for that as well. And prior to that, I worked on the Aqua Aura and Terra satellites that are run by NASA. And all of them are primarily weather satellites and climate study satellites as well. And on this lead slide, I did my best to find a good illustration of the types of satellites that we use for our meteorology and climate study. And you'll see on that cloud of satellites that are real close to the Earth, those are the low Earth orbit satellites. Those are the ones that I've worked on. And out here in this rather, I don't know what word, we'll go with big, rather big ring out here, those are the the geostationary satellites. And I have colleagues that work on those, but I haven't worked on one of those yet. I hope to change that soon. And I've given this presentation a little bit before for Dr. Cardona, and I updated this one so that it more focused on the meteorology side and less on the engineering side. So, with that, we'll jump into what we've got. If my computer will play along. There we go. All right. So, a quick overview of the science and technology used on board these satellites is that we've essentially got multi-channel optical sensors that observe various wavelengths of visible and invisible light. I
Sorry, Joey. For some reason, you're not showing your presentation. Let me see if there's something going on here. Um,
try resume share. Do I have to get out of presentation mode?
Maybe unshare your screen and share it again to see if that helps.
Yeah, give me a sec. Come on, computer.
So I can
So
see your second slide now. I don't know. Maybe it might be just better to leave it this way.
okay, we'll leave it this way, and they can see all the ugly on the slides. That'll be fun. But all right, cool. So, were you able to see that first slide, or should I go back?
You're fine to
Okay.
pick up here.
All right, cool. So the science, as I was saying, the science and tech behind satellites and the instruments that we put on the satellites to do all the sensing that they do is essentially just absorbing the light emitted from Earth. And the optical sensors observe various wavelengths of visible and invisible light. I'm not sure how familiar you all with the are with the electromagnetic spectrum, but essentially all things emit light. You and I are emitting light right now in the infrared spectrum, and probably a little more. The light that we see with our eyes is in the visible spectrum, and a lot of the light that is used for weather forecasting. For whatever reason, the word meteorology doesn't like me, but for weather forecasting and climate changes, they use visible, infrared, near and far, and microwave radiation to gather temperature information, pressure and moisture measurements, all that sort of fun stuff. And a quick overview, going in a little more depth of that, is presented on this slide, displaying the infrared or displaying the electromagnetic spectrum. Let me move this so I can actually see. Nope. You know what? Okay, Zoom, you can do it like that. So you can see, and at least so I can see what I'm talking about. And really, the sensing that our instruments on the satellites do basically from visible, so this part of the spectrum, all the way down through microwave. And the cool thing about this graphic is with the wavelengths that you can also see the corresponding temperatures that they can sense. So microwave, with the microwave radiation that we pick up, we can go all the way down to 1 degree Kelvin if we so chose. But it's a good thing that we aren't that cold on this planet. So it gives us really the full range of temperatures that we'd like to see and that we want to study and trend over the course of several days and over the course of the several swaths that the satellites cut through their time that feeds into the forecasting models. So, moving along, um, the way these sensors are built, and again, this is a huge simplification, is that they are made of different materials that absorb, react, or emit or emit different wavelengths of light. And those different materials are used to then photovoltaically turn that signal or that reaction of theirs into an electric signal that is then recorded to our solid state recorders on board the spacecraft and then played back down through the ground stations from the spacecraft while it's on orbit so that we can then have that data here on Earth from that great vantage point of up in the sky. Um, Going back to the difference between low Earth orbit and the geosynchronous orbit satellites, quick, and this is just a quick note that the low Earth orbit satellites are about 824 kilometers in altitude, so they're pretty close, but they get a good view, and those are the ones that are primarily used for weather forecasting. The geosync ones, they're 22,000 miles away, and they are used for real-time weather analysis. So if I can go back a couple of slides, the picture that you see here, that is the full side in daylight of the Western Hemisphere. That was taken by one of our geosynchronous satellites, and that was actually one of the ones that was launched about the same time that J1 was. It was GOES R, and it's actually, I'm pretty sure that was a picture of the winter storm that hit us in 2016. And then over here on this picture, this is a picture from the predecessor to the J1 satellite, NPP, which also has one of the instruments that I'll be giving you more detail on in this presentation. And you can see that it's much closer. It's got a little bit higher res, but in these cloud patterns that you can see here, these trails, they actually are indicators of the path lines or the emissions from the shipping lanes, and that's one of the things that our satellites are used to help analyze as well. Um, any questions here on this overview before I go into the specifics of each instrument?
Yeah, why on the first slide or the second slide, why those trails that you were talking about, why are they white? Did you like choose that color, or are
No,
they actually like that?
that's that's the color that they show up in the in the VIIRS instrument. The VIIRS instrument is the one instrument that we have that takes pictures in the visible range. So in the same way that we'd see the colors, or the way that we would perceive the colors, that's how the instrument perceives it. So given the way, or given that, that's the colors that are being seen.
Oh, okay. I thought that was like invisible to us, but then you plotted it as white. Okay, thank you.
No, honestly, that's a really good question and a good distinction to point out. um, yeah, in the later slides, I go through which pieces of the magnetic or the electromagnetic spectrum that each instrument are absorbing or are sensing, and then I get corresponding pictures too. So you'll be able to see how the things that are invisible to us get transformed in a way that makes it visible and digestible to us. Good question, though.
Thanks.
So I have an observation. So in the first picture on the second slide, those are chemtrails, right?
No,
No? So do you have to do with chemtrails? Like, do you have to do with like picturing and analyzing them, or you don't have anything to do with those?
We have to do with them, but the cool thing about chemtrails is that they're just water.
Okay, thank you.
You're welcome. Any other questions?
There are no questions on the chat.
All right, sweet. Then let's carry on. So, this is a picture of the J1 satellite, which is the one that I launched in, or I helped in the launch with in 2017. And J2 is very similar, except we don't have one of the instruments that I'm also going to talk to you about. But without going into too great detail on the engineering side of things, which is my specialty, the instruments are placed on the Earth-facing deck of the satellite. So all of them are down here on the bottom so that they can receive the light from the Earth, sense it, analyze it, and record it to all of the engineering equipment on the top. That is essentially just a super complex robot and computer all in one. And all of the computational stuff that happens there and further telemetry that is recorded gets recorded to several different solid state recorders on board, and then that information then gets transmitted either by this antenna or that antenna. Oh wait, nope, got it wrong. That antenna or that antenna in the Ka band, so that's of radio waves, through to our ground network or to the tracking and data relay satellites that are also in orbit, which allow us to get the satellite telemetry and satellite communications and commanding done and transmit the data. So, since we're talking meteorology and not engineering too heavily this time, I'm going to fly past this, and I think I'm coming back for another engineering talk later in the year, and I'll be able to spend plenty of minutes on the slide. But oh wait, I didn't talk to you about the instruments down here. So the instruments that I'll be going through are ATMS, CRIS, VIRS, OMPS, and Sirius. Now all of those are acronyms that I'll give you the definitions for, but it's a full suite of instruments that work in conjunction to perform climate studies and weather forecasting. And every different satellite has a different instrument suite based on what the mission's objective really is. So for me, I do weather and satellite or weather and climate study. There are reconnaissance satellites, obviously, and there are communication satellites that are all out there, and they all have different technology on them depending on what they were designed to do. So going into our instrument suite, ATMS is short for the Advanced Technology Microwave Sounder. And over here on this side, you have a picture of our nice, pretty instrument sensing brick. It's this right here and these right there are actually the optical holes or the optical fields through which the instrument senses or receives its data. And this is the primary instrument used for meteorology. Sounding and sounder instruments and sounding data is what is used for near-term forecasting. So anytime that you're watching WJZ or checking out AccuWeather, the data that they use to drive their forecasts comes from a sounder instrument or many sounder instruments to give you the 5 to 10 day forecast. And that's why this one is so important, and that's why I have a job right now, is because a lot of our weather satellites are aged, and they want to get more refined or more high res instruments up there. So this is the next gen of those long-standing sounder instruments, and if you just Google sounder instruments, you can find a lot more information on them. But it collects microwave radiation from the Earth's atmosphere and surface, And if you remember from a couple slides ago, the microwave radiation is what we use for temperature sensing primarily, because that is what we can sense or what we can determine whether something's, freezing, 90 degrees, all that sort of stuff. And what was I going to say in addition to that? I hope it'll come to me. But in addition to the temperature profiling that it does, it also provides data on the hydrologic cycle. So the water cycle, different rainfall rates, snow and ice formation, because that's also different, reflects differently, and sends out different temperature sensing or different temperature readings for them to be sensed. And it works in conjunction with the CRIS instrument, which I'll be going over in a couple of slides. But here's some examples of the data collected by the ATMS instrument. Over here on the left, you've got a temperature profile at a constant pressure for the entire United States over the course of, I think a single day. Quick note, these temperature profiles are essentially an average temperature profile over the course of the 4 hours it takes for our satellites to gather a full swath that collects all of the U.S. data. And when I say swath, I mean it's just the visual path that the instrument can see at any given pass. And our satellites are conducting 16 orbits a day. So even though, so in the first orbit, it might come down and catch essentially all of the mid-Atlantic. And then in the next orbit, it'll come down and catch a lot of Middle America. And then in the third orbit, it'll catch the Rockies and the Pacific. And then all that information we compile together and give ourselves the picture of the average temperatures over that 3 to 5 hour period. And it's not just limited to the United States. These satellites are taking these measurements around the entire world, as you can see here in this on the right side of the slide. And these are, again, just temperature profiles. So the brighter the color you see over here, the higher the temperature. So Antarctica, bitter cold, really dark. Let's see if I can pick out Sahara Desert, nice and bright. Same with Saudi Arabia and a lot of the northern Indian Ocean. So all of that data that we collect, it's brought down and sent to a worldwide community of meteorologists for analysis and forecasting and climate study. Any questions on this instrument before we go to the next one? Cool. So, the Crosstrack infrared sounder. As mentioned before, this is the secondary instrument used for meteorological study, and it collects infrared radiation from Earth's atmosphere and surface. Now, infrared is the next category up on that electromagnetic spectrum. So it gives us some temperature reading, but the great thing with infrared is it also gives us further insight into water formation and water formation in the atmosphere. So the microwave radiation that ATMS is sensing is transparent to clouds. So ATMS looks through clouds and can see sea surface, and it can see the land surface and gives us those temperatures. The infrared light that Chris is sensing is opaque to clouds. So it cannot see through these clouds, but it does give you the temperature reading and corresponding pressure and moisture reading of what's in those clouds. And that information combined with the ATMS information gives us a full 3D profile of on the attitude of what the temperature, pressure, moisture, and really the air makeup. Yeah, the air makeup at a basic sense, because we've got another instrument that does a better job at that one. For those weather forecasting profiles. or those weather forecasting models. It also provides data on the greenhouse gases and provides long term data. And when I mean long term data, I mean data that is collected over a long period of time to then allow for trending and analysis of different climate phenomena. So, anytime you hear a meteorologist talking about El Nino or La Nina, they're likely using infrared data coming from this instrument. And of course, climate change. So, this was the best picture that I could find for Chris that really shows you all of the information that it's giving you. Um, this is a 3-day composite image of the sea surface temps, and really the sea surface temperatures, the land surface temperatures, and the cloud top temperatures. So anywhere that you see colors down here in this red and magenta range, that's where it's bitterly cold, and very likely that's where it's showing you the temperature in a cloud top rather than the temperature on land, because as you go higher in the atmosphere, temperatures tend to drop pretty precipitously. But if you look at your ocean temperatures and even your the temperatures on land here, it gives you that sort of that full profile that I was referring to in the previous slide. And it also allows you to analyze, like, oh, if we look over here, we've got bitter cold temperatures that are showing up around the equator over here in Polynesia and Melanesia. That must be a lot of storm activity. Hooray! We found it. Yeah, I think that's what I got here on Chris. So next up, we have the Ozone Mapping and Profiling Suite. This one is, it says it right there in the title, but I'll keep talking. It collects total column and vertical profile ozone data. So this instrument and many instruments like it are what is being primarily used to study the ozone hole. And the other thing that our study with them is that the thickness of ozone at any particular point also provides a lot of UV reflectivity. So if the instrument says, "Oh, ozone is thin in these areas at this time and it's changing at this rate," that's how the meteorologist can give you the UV warnings in the summertime or whenever that might be useful to you, so that you know to avoid direct sunlight on those days. It also measures the other atmospheric particle densities or particle makeup in those columnal measurements that it gives you. And so that includes not just air, but volcanic ash, sulfur dioxide, freon, any other level of pollutants that they can pick up and analyze and let you know the distribution of them from the surface of the Earth through the altitude of the satellite. And it's a pretty cool instrument. I like this one actually a lot. So here's some of the data, and this is really the same picture presented two different ways. The ozone hole, or the hole in our ozone layer hanging out down here in the southern hemisphere over Antarctica, it's getting better, but it's still there. And really, you can see this projection and all that information captured on this side of the picture as it's showing up as essentially zero. And then you have your ozone makeup for the rest of the Earth over the course of this day, all over in these areas. And as you would expect, population dense areas and metropolises have thinner ozone. So if you look over here where Southern California is in Los Angeles, that's a famed source of ozone depleting particles. Their ozone layer is thin. Same thing up here with the northeast of the United States. Fortunately, all that tends to flow up on the Gulf Stream and affect Canada more, but it's still a worldwide problem. Yeah. Any questions on those last two?
Wait, so red is less ozone
Correct.
and blue is more?
Red is, yeah. From what I understand, red is like you. I think you want the blue area. If you have zero or red, that means you're probably thinning up. I think. Again, this
Well,
one's this,
no, actually, sorry, Jerry, but
yeah, go ahead.
the ozone, if you look at the scale below, the higher numbers are the thickness of the ozone. Um, so to the smaller Dobson layer would be the blue.
Ah, thank you, Professor. See, that's why you're teaching this class, and I'm just flying the things.
So both the maps are they showing the same thing, but from a different
Yes,
angle?
same
Okay.
thing, different angle. This is all the ozone layer uh, uh, projected onto the world onto that screen, and this is essentially that same information projected onto a representation of the Earth, and it's a 3D representation. And if I were better at embedding things in presentations, it would be interactive, but I'm not. So I'm sorry.
Okay, cool.
Just to elaborate, in case you were curious, basically each Dobson unit is equivalent to a millimeter of thickness. So that's why I was referring to the larger numbers being a thicker layer. The average is about 300 worldwide. So the areas that are seeing 600 are doing all right. But we are the source of the pollution. It's just that it ends up going into the South Pole because of how the jet streams move and how the air moves and circulates. It has to do a little bit with the Coriolis effect as well.
I just learned something. Thank you. Anything else? All right, cool. So, moving on to the visible infrared imaging radiometer suite. Um, this is the one that gave us the picture that had the shipping that we could see the shipping lanes because it's sensing in the visible part of the infrared spectrum or the electromagnetic spectrum. Um, these visible images we are used for predicting or for using in conjunction with ATMS and CRIS data to get a better sense of what the sea surface temperature is and the ocean color is all over the world. And the ocean color is indicative of water quality, and also the sea surface temperature and ocean color are huge inputs going into hurricane forecasting. The other part is that VIIRS just takes very pretty pictures. It's honestly a running joke on my at my job that VIIRS is only on board to take pretty pictures. But it takes very good pictures, and it does more than just take pictures. It does that in the visible spectrum for both day and night, and primarily in the infrared spectrum for nighttime imaging. And the I don't what I guess I just didn't finish that bullet point. I'm sorry about that. But the radiometric data is back in the radio wave side, and I believe radio waves are. I'm gonna have to go back and check. Excuse me. Ah, so radios are down here with microwave. So I think they're providing more granularity on what the microwaves are providing. But take that one with a grain of salt because again, this now we're getting a little out of my depth. I'm more engineering and less forecasting. But of the pretty pictures that VIIRS takes, here some of them are. On the left, that is actually a picture that was captured by NPP, so the precursor to J1 of Hurricane Maria, and it's if you're a storm scientist, it's magnificent. But if you lived in the Caribbean at that time, it was just a nightmare. And but you can see the cool thing about this picture I like is that you can see the gradient and the change of day going right through the middle of the picture, basically. Because on this side, there's still solar radiation illuminating daytime for that part of the Earth, and it's actually dawn for them. And this is on this side, you can see Florida well lit, uh, coming towards the end of its nighttime. And as the Earth rotates in this direction, dawn will make its way onto Florida, and I just think it's a really cool picture that captures the capability of VIIRS to get everything all at the same time. And the composite data, or the data that makes up these sort of composite images, also gets overlaid in other ways to make other pretty pictures, like the famous black marble picture that NASA likes to throw up to show how cool our science is. Shameless plug. Um, let's see. And then we get to the cloud and Earth's radiant energy system, the Ceres instrument. Now, the satellite that I'm working on now actually doesn't have a Ceres instrument on it, and it won't, but the follow on will, and the one that I worked on beforehand does. Um, this instrument is used to collect data on cloud height, thickness, and the particulate size making up the clouds. Um, Dr. Cardona is going to have to give you more information on how that relates to weather forecasting. I've only got I'm a novice at that. She's got all the info for that one. But the cool thing that I think this instrument does for us is that it collects data on the energy, the solar energy, reflected by the clouds away from the Earth, which is key in maintaining the overall temperature of our planet. Um, and that radiological information, or that radiant information surrounding the radiant energy, is used in climate studies more often than not, and it also is used to validate meteorological models, which calculate the cloud's effect on the planetary heating and cooling. And the studies are showing that clouds primarily provide a cooling effect more than anything else, which is great. Um,
To add to
the
that, it's because they have about 50% reflectivity. So if there's clouds in the sky, half of the sunlight or half of the energy that is coming down is reflected back out into space. Now, if the clouds are there at night, that actually provides a warming effect because the infrared radiation that's bouncing back out from Earth is bouncing back down as it hits the clouds. So at night, it provides a warming effect for us, which we need. And during the day, it's cooling, which is helping, um, when it's warm out. Not right now. We would like it to be warmer, wouldn't we? But
Man, these last couple of days have just been heaven. But that's me. Let's see. The data also can be used for assessing the radiative effects of natural disasters. So, as the solar energy is either reflected by the clouds or makes it to the surface and then is either reflected or absorbed by the surface, depending on the absorptivity, reflectivity, or transmissivity of the surface, or the piece of Earth surface that energy hits. Uh, Ceres can provide some insight into how that is playing out in those localized areas. And in the case of volcanic eruptions, volcanoes will spew some ash or sulfur dioxide into the clouds or into the atmosphere. Ceres will pick up on the change in energy output or energy reflected at that area. And the same principle applies to floods and droughts, but volcanoes are just more interesting to me. Uh, and this was the best image I could find for some of the series stuff. Now, if oh, okay, all right. So, what this is a what was this? This is the shortwave cloud radiative effect. Basically, anywhere where it's darker, if I remember, should have brought my notes up with me. But anywhere where it's darker is showing that there's more, or I think there's less reflectivity happening there than there's anywhere that there is lighter. And that's essentially what Ceres is doing for us. It's just measuring the amount of energy that is reflected by the Earth, whether it be through its clouds or through the characteristics of the sea or Earth's surface, and how much energy comes from the sun. We know how much about how much energy is coming from the sun, and we're determining how much energy Earth is radiating out on its own. And yeah, I think that wraps me up. So I hope you all liked it. I hope it was informative and not too confusing. And thanks for taking the time to attend. Any other questions?
Do all of the satellites orbit in the same direction?
No. Great question, but no. Or not even but no. The answer is no. Let's come back all the way up here. And let's move this so I can see what I'm presenting. So the geosynchronous satellites orbit in the same direction. But that is because they're geosynchronous, and what that means is they are in lockstep with the Earth's rotation, meaning they, relative to the Earth, they stay in the same position. So this satellite here that, let's assume, is looking at the Arabian Peninsula, as the Arabian Peninsula rotates and goes throughout its day and night transitions, that satellite is following it the entire way around and always just looking at it. So everything out on this orbit belt is moving in the same direction, and in this picture, that would be clockwise. All the satellites down here in the low Earth orbit cloud, they are certainly not going in the direction, all in the same direction. Some are what's called descending node, which means as they come from the night side of the Earth into the day side of the Earth, they're doing it at the North Pole and descending towards the south. Some of them are ascending node, meaning as they come from the night side of the Earth to the day side of the Earth, they are ascending upward from the north. I don't have any information on what percentage of the satellites are assigned to or have that particular kind of orbit, but I'd imagine it's a pretty fair split. The other orbit information that really matters for this one is what's called the inclination of the orbit, and that's a measure of the angle of offset between the orbit of the satellite and the Earth's equator. So if you have an orbit inclination of 0, you're orbiting at the Earth's equator. But if you have an orbit inclination of 90 degrees, you're essentially orbiting north to south constantly. My satellites have inclinations that are close to 90. They're polar satellites. I think they're at 88 degrees about. But they chose that inclination so that as they make their orbit, they'll come down and hit a different swath or section of the Earth over the course of the day, so that they can get more data on the full Earth, on the full set of Earth's surface more easily. That's the long answer to your question.
If it's not on a 90-degree angle and it's on an 88-degree angle, will it migrate over time?
Yeah, but you want it to, because you want it to. Well, when you say migrate, do you mean that will it transition relative to the Earth, or do you mean will it drift either towards 90 or towards 0?
Like drifting towards like a higher or lower angle.
Yes, that does happen. That's more of a result of space weather and orbital decay than anything else. The orbital decay is a result of drag forces that come from the where do those drag forces come from? Solar weather, solar wind. Um, the satellites up there are subject to, like, they aren't protected by an atmosphere, so they get a lot more of the electromagnetic radiation and any particulate matter that's the sun is also spewing out, like electrons, neutrinos, all that sort of stuff is still hitting and passing through and affecting the consistency of the orbit. It's a very slow process, but it is something that needs to be monitored so that we can maintain the proper inclination of our orbits. And on my missions, at least once a year, we do what's called an inclination adjust maneuver, which re-angles the satellite. Like, while we're doing this, we're not taking any weather data. We change the orientation of the satellite so that the thrusters fire at a certain direction, either lower our interest lower our inclination or increase our inclination, depending on how the solar weather has affected our orbital path.
Thank you. That's really cool.
You
You're
have a
welcome.
question here on the chat says, has there ever been a time that the equipment fails and is unable to communicate?
Yes, yes, absolutely. I on the first satellites I worked on were three satellites that were all in the same constellation, and the oldest of the three was the only one that had all five instruments working as they were intended to work from the day that they were launched into space. Um, the let's see, these satellites are Aqua, Aura, and Terra. The Amzari instrument on Aqua, which is used, it's a sounding instrument, but that had a mechanical failure following launch, which limited its the way that it rotates to gather the information as it goes across, and it can't reach its optimal rotational speed. So they have it set to rotate at instead of 40 RPMs, it's rotating at 2 RPMs, which is much slower, but it still is providing useful weather data, but not at the same granularity that they would have gotten if they got the full 40%. On the Aura satellite in that trio, the Tears instrument, which is another sounder, but I forget what it stands for, and the uh, HIB instrument, HI Bravo, not HIV, but what is it? The humidity in something or other, but it's measuring humidity. Both of those got launched, and due to oversights, are essentially just bricks on that satellite now. But there are other instruments that are taking data, and those are examples of instruments that could not be recovered. Uh, on the satellite on J1, our VIIRS instrument, um, we noticed some anomalous behavior during the commissioning of it. And through analyzing the telemetry, we realized that there was a moisture pocket affecting one of the lenses that had gotten frozen. Essentially, there was some water in there that shouldn't have been, that didn't get completely evaporated as we opened up the instrument or as we heated up the instrument to make sure that the lenses were clear and ready to sense things. And fortunately, the VIIRS engineers were able to come up with a series of commands that we could send to the instrument to provide targeted heating to essentially break apart that buildup. And we were able to get that VIIRS instrument up and running and rolling and providing pretty pictures for everybody to this day. So, short answer, yes. Long answer, it happens in any number of ways, and it leads to a lot of creative solutions or just having bricks in space.
Joey, what's the ballpark price of each of these satellites? The American taxpayer wants to know.
Well, rest assured, American taxpayer, your taxpayer dollars are going to a great cause.
Indeed, I agree.
The ballpark, it depends on the mission and the really, yeah, it depends on the mission and depends on the what, like everything that's going into the satellite. For the ones that I walked you through today, J1 all told cost on the order of $1.7 billion, something like that. Yeah.
Okay.
And J2 is less than that, but that's more due to the fact of the way the contracts were structured. It's fair to say that the instruments themselves cost on the order of tens of millions. The spacecrafts which house the instruments cost on the order of hundreds of millions. And then the operational teams like me who maintain, monitor, and fly the things for our employment, those all cost on the order of tens of millions as well. So through their lifetime, you can imagine a satellite costing on the order of billions of dollars, not tens, but like billions. And billion with a B is a lot. But the cool thing about that is that billion with a B is spread over the course of the life cycle of that satellite. And all of these satellites are designed to last for, provided there are no problems with launch or the bricking of the instruments, they're designed to last for 7 to 8 years before they're considered to be decommissioned, which means being pulled off of orbit. And a lot of satellites, the vast majority of them go for far longer than that 7 year time period. So you get the return you get for your billions is massive. The first satellite I worked on, Terra, it was launched in December 15th, 1999. So Terra is what, 23 now? It's getting real close to being able to rent a car without the added protection. Aqua and Aura were launched in 2002 and 2004, respectively. J1's been up since 2017, so not a great example there. J1's predecessor had been up since 2005.
Wow.
Let's see, like the Hubble's as old as I am, maybe a little younger, but Hubble's been up there for close to 3 decades and is still providing great, excellent astronomical science data for the astrology, or not the astrology, the astronomy community.
Yeah, no, good stuff. And you think of the disasters that are averted and the billions of dollars that disasters result in. So the ROI is pretty high.
Oh yeah, the ROI is incredibly high. Actually, to tell a coworker's personal story and why he loves being in this field. He is from just outside of Galveston, Texas, and if you're on the Gulf of Mexico, you're in hurricane territory. And
Yes.
he's older than me, so I forget this, but he's about to retire. His grandfather was around for the hurricane in like the early 1900s that absolutely decimated Galveston. And to hear him tell it, his grandpa was telling him, it was just like, hey, one day it was fantabulous, and then we went to sleep, and then the next day it was like we were at war, and then we stayed at war for a long time. And if you think of it from that point of view, the information gathered from weather forecasting and averting crises like that is priceless.
Sure, sure. I grew up in South Florida, and of course, the famous hurricane was, I think it was 1935 or 36 down the Keys that tore up the railroad that went down to Key West. Hundreds of lives were lost because they didn't know, and so
no idea.
Right, but they don't have a name for it, but they just said the hurricane of, and there's a memorial on Isle Morada to that devastation. So great presentation, Joey. Thank you very much. I'm an engineer myself, and thoroughly enjoyed the presentation. Very, very informative. Thank you.
You're welcome. Thank you. Yeah, I'm doing another engineering one later on, and I've got to tune up those slides. But thank you. This is great feedback.
Yeah, you have a time frame when you're gonna have that presentation?
Christina, what day did we go with?
We haven't scheduled one, so we'll touch base, and I will let Jamie Alvarez know. I usually forward these links to him and let him know that.
Okay.
To let all of you guys know in the engineering department.
Great. Thanks again.
No problem.
No problem. You're welcome. Cool. Yeah, anything else?
Doesn't seem like it. Well, thank you very much, Joey, and this was a great presentation, and we'll touch base about your next event after this. I'm going to stop recording here, but thank you everyone for showing up, and if you have any further questions, you can reach out to me at ccardona@ccbcmd.edu. Thank you.
Thanks, everybody. Take it easy.